Okay, lesson 7. All right, we're moving into inverse functions and one-to-one functions. Just the two, good. So inverse functions, we remember these hopefully a little bit from last year, and then in 1010 we got to work with them a little bit. But in inverse function, we always notate inverses with a little superscript. So you guys, does this look familiar to most of us? We've seen it before. So f to the -1, we'll usually like f of x. We still use function notation. And then the f has a little like superscript -1. Okay? So let's pretend that it's a function that contains all the ordered pairs of f with the first and second coordinates switched. For example, let's pretend on my first function f, I have a coordinate at AB. BA is contained in f inverse. It's just swapped. Don't change signs or anything. It would just be them swapped out. Also, the domain of f equals the range of f inverse. So you'll notice as you guys compare your domain and range of f, you'll notice this domain is going to match the range of f inverse. Okay? What was an x on an original function, its inverse is going to be their y's. Okay?
So will the range match the...
Correct, yep. Sound good to everybody? So in a nutshell, anything with x's and y's is swapped. We'll get to it graphically, but graphically that works out that they are kind of like a 90-degree turn and a flipped version of each other graphically. And we'll talk about that and how we compare inverses on a graph in just a minute. All right, now for easy like disjoint points, let's just kind of do our list of values that would be in the domain. So how many? Someone hurry to yell out all the domain of f. 0, 1, 2, 3, 4. Good. And they are, you don't get to do an interval because they're separate points. So, good. The range is what?
0, 2.
Very good. So you're looking at all the y's, right? Now let's rewrite this so that we have the set for the inverse. So what would the inverse have?
0, 0, 2, 1, 4, 2.
Very
6,
good.
3, 8, 4.
Good. All we did was swap them, and I don't have any negatives involved. That's when it really messes with people's minds, is they kind of like want to switch out and make things not negative. So I wish we had some negatives on here, but this is just a good setup. So 6, 3. Where are we? 4, 8. Okay.
8, 4.
I mean, thank you, 8, 4. Okay. So now when I go and list my, and the reason why we do such a basic representation is it just goes to show how the domain and range. It's a good way to see you guys organize the domain and range. So this one's domain is now at 0, 2, 4, 6, and 8. And this one's range is now at 0, 1, 2, 3, and 4. So now that you've seen like a really easy representation of it, you can now see that this domain is matching this one's range, and this one's range is matching that one's domain. We're not always going to have it this easy, just as an ordered pair, but this is just a good way to kind of get you kind of going with it. All right, you are asked this sometimes as quick hit problems. What's f inverse of 8? I might even give you just that. So the test question could say, hey, here's a function with some ordered pairs, and we're asking you to do f inverse of 8. 4, right? And that value, anytime they ask for function notation, it's just saying y equals. So you're always going to write your answer as if you're saying like, hey, y equals 4. Or, yeah. Okay, do you guys feel pretty good about that? Okay. To have an inverse, they have to be one-to-one functions. So no two elements in the domain. So when we did a mapping diagram back when we learned functions, do you guys remember this? When we did those mapping diagrams on like day 1. And it's okay, like let's say 1 maps onto 2 and 3, 4 can map onto 5, right? So when you guys are thinking about ordered pairs, I'm not allowed for 1 to map onto 2 different places. So at x equals 1, if I have an output at both 2 and 3, that is not a function, right? But let's take let's take the 4, maybe, also mapping on to, well, let's actually do another value. Let's bring in a 3. Let's say 3 maps onto 2. That's allowed. Like I can have 2 things map onto and it still be a function. So I could have a value here and it still be a function, okay? However, think of those functions that have 2 outputs in the same spot. Those are parabolas, and this is representing a function. However, it is not a one-to-one function. So even if something's a function, they're not always one-to-one. Parabolas are a perfect example. I can have 2 different outputs that reach the same spot. So as a parabola is, it doesn't have an inverse. What did you have to do? Honors kids did this. Do you guys remember you doing anything to something like a parabola so that it had an inverse? Do you guys remember restricting its domain so that it has an inverse? Do you remember saying, oh, if I just take x is greater than or equal to 0, if I just take this portion of the graph, I can now find an inverse. Does anybody remember that? No. And if you don't, it's okay. But if I restrict its domain and make it one-to-one, now it has an inverse, which its inverse is a radical. We already did this on the parent function thing, okay? So for things to have inverses, they have to be one-to-one. I would not be able to graph the full inverse of a parabola because it wouldn't be a function, right? It has to be one-to-one. And that's what one-to-one means. So there's something called the horizontal line test. We're used to functions being a vertical line test. Well, if you want to check for one-to-one functions, there's something called the horizontal line test. And graphically, it's really easy to see if things are one-to-one. So no 2 elements in the domain can correspond to the same element in the range. So you pretty much make sure nothing repeats. None of your x's and none of your y's like repeat, essentially. Okay. So looking at example 2, do you guys think that this is a one-to-one function? It is, right? Everything is unique. And no 2 elements in my domain map on to the same. Think about a parabola, like -2 and 2 both map onto 4, right? It's not something like that. And then, so let's just quickly evaluate this. What would you guys say f of -2 is? Good, how did you say 2? You went to the y, right? So you guys imagine f inverse would have been -2, 2. So then when I want to find f of -2, I realize it's 2. Okay? All right.
So would we just like on the test, would we just write equals 2?
Mm-hmm. Yep, just the output value. Good job. And then back up example 1. When you guys look up at example 1, do you guys think that it is a one-to-one function? Yeah, everything's unique, right? There's no 2 x's that map onto the same y. So think of it that way. I have a problem. Did any 2 x's map onto that? So you guys would have said yes on that one. All right, let's just quickly look graphically. 1-to-1 on a y equals x squared. No, right? It does not pass the horizontal line test. Because I told you f of x, f inverse is just a turn and flipped version of that graph. So if this was like a turn and flipped version of that graph, it would not be a function, and therefore it's not 1-to-1. Okay, and we can't find inverses of things that aren't 1-to-1. What about y equals x cubed? Does this one pass the horizontal line test, and is it 1-to-1?
Yeah.
Yes. All right, now algebraically, this might be the tricky one. What do you guys think algebraically, or not even algebraically, but like an expression or an equation? Do you guys view this as 1-to-1? And why do you think it's not 1-to-1? Did you finish that quiz?
Yeah.
Okay. Oh, you did? Oh, I thought that was it. Why did you say no?
I just guessed.
It's a good guess. Anybody have like a reason? I'll go with, I think her hand was up first, but if she's wrong, I'll go to you, Kai.
The exponent is like even, which makes it like this.
Good job. You are introducing or remembering it's next unit. We actually talk about parabolas next unit. But it is important to realize that 4th degrees, squareds, and all that kind of behave the same. And so whatever the case, it's still they're both going off to infinity, right? It's an even function. So when you guys view this as an even function and you realize, oh, even functions are symmetric on both sides, how many of you guys, did anybody do this? Like, hey, it's an even function. Did anybody think of it as an even function that way? Or did you just view it as a graph? So algebraically, we weren't even on neither. So I could have been like, oh, even functions definitely aren't one-to-one. That's another way, okay? Let's go ahead and move on to the next side. We're gonna go to example 4. True or false? If a graph has two x-intercepts, then it is not one-to-one. True or false? True. Not one-to-one, because two x-intercepts do two x-intercepts pass the horizontal line test? No. So true. It is not a one-to-one function, because they would not work. Okay, let's move on to here. Okay, you guys, this is your strategy. We just learned how to compose last time. We learned how to plug something into one another. There was a problem I chose to skip over in your guys' notes, and if we need to get to it, I can show it here, so I probably don't need to go back and do that one. Don't tell me her copy. I don't know what to do. I have sent copies in my exact files. Oh, you have it. Okay. Did anybody get shuffle their notes here?
I fear I might have.
Dang it. Does anybody have extra of something that they? Is yours going in order? So you would notice on. Oh, this is 8. I have a.
She has it.
What? Oh, okay, good. That's okay. There's days where I'm like, now there you go. You scared me. Like, no, don't tell me I wasted another $15 in copies. Okay, this is how to show functions are inverses. And I forgot to write that in, so when I copy and pasted everything, some things got shuffled. So inverses are reflective over the line y equals x. How many of you guys remember this from last year? It is in Math 3. We talk about it. Do you remember how they're reflective over the line y equals x? Do you remember that?
Yeah, actually.
So when you guys compose them, one and the other, you actually get the same output. This is the only time it's going to happen. When you guys probably noticed on your homework, when you go to plug f into g and g into f, you always got different outputs, right? They look different. But when they're inverses, everything just kind of simplifies out to x. And the reason for that is because they are symmetric over the line y equals x. When you see them on a graph together, which we'll look down here in 1 second, they are reflective over that. So let's hurry and do it algebraically, and then we're going to check it out graphically. Your homework you guys might be asked to graph a function and its inverse and put them on a graph together. And they've actually mixed it up on what they ask about inverses, but they do ask inverses somehow. They sometimes have you sketch them on a graph. They sometimes just have you do this, verify their inverses, or they sometimes just tell you to find an inverse, which we're going to practice all of it, okay? So if I want to verify that f and g are inverses of each other, I'd take what? I take f of g, and I see what happens and see if I get this result, okay? So let's go ahead and do it. Why don't you take a moment to try it yourself, and let's just kind of compare and see if it works out. Good. Did you guys get x when you were done? Good. Let's go the opposite way. If they truly are inverses, it has to work both ways. So now I take g, and I replace f into my g, which is an x minus 4 over a 7. And then we kind of just see if they simplify out. Now luckily, this 7 is up in the numerator. Those cancel nicely. And so this turns out to be x minus 4x plus 4. So how many of you were able to get to the same point that I did, that realized they are inverses? So here's a check also. You guys can use to check. When you guys are asked to find inverses, if you take them and quickly plug them into one another, you will know, oh yeah, hey, I did it right. I was able to get x, therefore I really did find my inverses properly. Okay? I'm going to try my best to keep that on the screen, but I just want to go down to this graph for a second. So because I said the graph of f inverse is the reflection of the graph across the line y equals x. So if I had a value over here at AB, let's just put numbers to it so we can kind of see. This looks like it could be at like 1, 2, and then maybe 2, 3. So this looks like if I had a value at 2, 3, The other one has a graph at 3, 2. So they are definitely, they will always have values. It's a little tricky when the graphs do a lot, but if you guys take these and you reflect them and like fold them over the line y equals x, they would overlap on one another. And so that's what inverse functions look like graphically. Now, how do I do this? It's way straightforward, really, really easy. If we just simply say to you, graph its inverse, you guys make note of a couple points and then just switch them. Even if the graph does a lot of crazy things and you guys want to be able to graph their inverses, you guys can even take decimal points and be like, this one's at about 1.55.4, you know, and like you can even switch those out. Now I like to do obviously ones that hit the grid really nice and equal, but you guys could have picked out more points and estimated more to be able to graph their inverses. Okay, so what I would do is I would take some coordinates and I would take the original function. What's this coordinate here? This didn't graph very good. Sorry guys. That's the y-axis. I'm not sure what happened. So that's the y-axis. So what's this coordinate? What's this coordinate right here? -2, -1. So I should, on f inverse, if I was plotting its inverse, what should I have a coordinate at? -1, -2. Don't change anything with the negatives, right? Let's do this other one. What's this other coordinate? Not 0. -1, 0. So it's inverse. Oh, maybe you were already doing the inverse. 0, -1. Is that what we have? Where did my first one go? -1, -2. Okay. What's this other point? These ones are decimals, and I'm like, I don't like that one. So what about this one? 2, 1. So I should have a value at 1, 2. Okay, so when they crisscross each other, it does get a little confusing. So let's just connect the dots like they did. And if I were to draw the line, y equals x, does it look like they are inverses of each other?
Yes.
Okay, so that's your check, is do they look like I could fold them over that line? Okay, we are going to move on to being able to find an inverse algebraically now. And here's your step-by-step on this next page. Let me pause for a second to get some people caught up. Okay, do you guys see this box on the top of the next page? Okay, finding an inverse. If I ever have it as f of x, I'll usually switch my f of x to a y, just because the y is a little less complicated. It's not a mandatory step, so this is kind of an optional step. I usually switch to a y. I'm going to use a y. So if I was given this and I want to find f inverse, I might rewrite it as y equals 2x minus 4. Sound good so far? Some teachers teach this differently. Some have you solve for x and then later switch things. I switch them now because we're so used to solving for y. So the next step I would say is to switch x and y, because that's what inverses are. Everything with x's and y's are opposite. So we're just going to switch the x's and y's. Now we're so used to being the ones to solve for y that that's what we solve for. So if we leave it and solve for x, I think it makes it more complicated. Do you guys agree with this method? I know some teachers taught you differently, so I don't want to like complicate things in your mind. Are you okay that we swap it now? Okay. So let's go ahead and solve for y. What would you guys do to properly solve for y? Have to add 4 first. Now what? Divide both sides by 2, right? So when this is divided by 2, you can write it as x plus 4 over 2. And then it usually says replace with f inverse if it was start as an f. So if it starts as a g, replace it with g inverse. If it starts as an f, replace it with f inverse when you're done. Now you guys are welcome to leave it like this, but what form, we're asking you to graph them now. So what form is easier to, what do we need to kind of convert this to make it like easier to graph? Slope, intercept. So I should put that 2 under both of them. So 1 over 2x plus 2 is also the inverse. So this is the inverse, don't get me wrong, this is the inverse. But if I'm being asked to graph, I'll usually write it in the slope-intercept form so I can sketch it. Okay, let's do the original in red. Let's do 2x minus 4. How do we graph linear functions that are in slope-intercept form?
Go to the y-intercept.
Go to the y-intercept, which is
4.
-4, and then what's our slope off of that?
2/1.
Up 2/1 in the positive slope direction, right? You guys all remember how to graph lines, okay? Okay. Let's do this next one in blue. How would I graph it? Y-intercept at 2. Slope is up 1/2. Good. Or down 1/2, but making sure it's positive. Ugh, sorry. Now, do these look like they're reflective over the line y equals x? Yeah, so that's pretty good. Now these are linear, so this is actually really easy in the domain and range part. I'll jump down and do one that does have restrictions so we can compare the domain and range part. But let's just go ahead and practice this. Let's go ahead and do f's domain. Linear functions domain are always what? All rails, and their range is also all rails. Sorry, we switched the domain and range spots on this one. So the function is all rails, and its inverse was also all rails. So this is not a great example. So one way that they do quick questions or true or false questions with inverses is they'll sometimes say, if the domain of this is blank, what is the range of f inverse? And so they're always using the domain of one. They don't expect you to graph all the time to get ranges. They want you to use the domain of the original function. We don't have to graph. You can do it. So we're actually going to do this one algebraically first before we even graph it. Okay? So let's go down here to one that has a restriction. So let's just pretend the question was just domain and range questions. Okay? Is it easy for me to know the range of something without sketching it? Not really, but it is easy for me to find what? Domain. So a test question might give you a function, and then it might say, hey, what's the range of f inverse? And how do I find it? The range of f inverse matches with what? The domain of the original f, right? So let's go ahead and calculate the original domain. How would you guys describe this domain? Sorry, that's supposed to say square root. What's our restrictions on those? Inside of a radical has to stay above or equal to 0. Okay? So x needs to stay above or equal to what? Okay, good. You guys, if we ask for set notation, are okay to say this. How do I write that in interval notation? Bracket, good, -2 to infinity. So if the domain of this is this, then I'm able to easily say the range is these would match, right? If this is -2 to infinity, what's this one's range? Good. Why do you guys think interval notation is the safest notation when you're working with functions and inverses? What would have I had to switch this to if I was using set notation? What's that?
If I flip the sign.
Close. Not really the sign, but think about it as domain and ranges. Your x's and y's. So x was above or equal to -2, so my y would have to be above or equal to -2. But if you use interval notation, it just is a seamless like, oh yeah, just copy it. Does that make sense to everybody? So it can be confusing if you're using x's and y's. So make sure you guys, I would just stick to interval notation myself. Okay? Now that's if they just ask a question without making a graph. Let's go ahead and do this still. Let's find an inverse just for practice. So let's go ahead and do x equals square root and switch it to a y plus 2. Now since this is a square root 2, what do you guys think its inverse is going to look like? Because they're inverses of each other. A squared. Who said that? It'll have a square. Okay? Alright, let's do it. How do I solve this for y? What do I have to get rid of? I do have to get rid of a square root by squaring both sides. Then what? Subtract the 2. So y is equal to x squared minus 2. So f inverse is x squared minus 2. So that's our inverse. Now here's where it gets a little bit tricky. It has to be a one-to-one function, and this is not a one-to-one function. So we have to realize that even though an x squared minus 2 looks something like this, we're probably only taking the what side for x is greater than or equal to 0, because they have to be one-to-one functions to even have inverses. Okay. And then when we go to sketch them, let's just kind of take a look at our domain and range and kind of put it together. So let's sketch the first one. It was a square root of x plus 2. What shift is that? From our parent function that had a value of 0, 0, 1, 1, and 4, 2. Do you remember this? I shift it where? Left 2, because our domain moved, right? Shift this left 2, and I'm sure we would be able to get those values hopefully after practicing the transformation lesson. Okay, let's now graph the blue one by restricting its domain though. So this has a value where quadratics are moved down to, right? So I had my vertex was here, so this is a parabola, right? It's now here. And instead of graphing this other side, we leave it off because it wouldn't be a one-to-one function if we did. Okay, are those inverses of each other? Awesome. What would you guys describe this one's domain as? It's tricky because looking at it, we would say all reals. But because we have to restrict its domain, it's what? It's actually 0 to infinity. And then what is its, well, we already did its range. So that matches this one's range, 0 to infinity. Okay. In a nutshell, are we recognizing relationships between inverses? That's kind of like the overall idea here. I might skip through these next two so we can move on to the next lesson, but I might do a part of them still. Okay. I think I'm okay on a cube. Are we okay sketching cubes? Are we okay finding inverses still? Okay, remember when you guys check for inverses, you plug them into each other. So just for the sake of making sure we know how to do it, if you guys ever want to double check that you found a proper inverse, remember how I can take this and plug it into that and plug it into this. So if I took f and plugged in what I thought was f inverse, I'm going to take my f, which is x plus 2, and in place of x plus 2, let's replace what we found, okay, which is x squared minus 2. So x squared minus 2, I'm replacing it in for my x, and then I have a plus 2. Well, when I kind of evaluate those, I end up just having a square root of x squared because the 2's cancel, which is just an x. And that's just one direction. So remember, it should always work out that way when you take the time to check that you found a proper inverse. Okay? So now I can take this one and replace it in here. And so I have an x squared minus 2 now. And I replace my square root of x plus 2. And they undo each other, and I end up getting x just fine. So that was just my quick check to make sure you guys know how you can always find an inverse by plugging them into one another. Okay, like I said, I'm probably going to skip this cubed one, x cubed plus 1. And then are you guys okay if I skip sketching this one since we have so much to get to, or does anybody want more practice with the inverses? I think your homework will give you a ton. Okay, I'm going to go ahead and just do example 11 really fast. Here is an example of a test question that I've seen. You take a look at it and turn and talk for number 11 really fast. 11 and 12. 11 and 12 are similar test questions. I've seen them on true and false. I've actually seen them on, I found it, in one way or another. It's your guys' big 10-point questions sometimes have an A and a B and a C. So this could be like an A and a B or a C question too. Okay? So turn and talk on 11 really fast and tell me what you get. And then turn and talk on 12 once you guys have that figured out. And let's see if we can find the answers. right, let's check into 11 and then I'll give you another 10 seconds on 12. Find the inverse of f. Oh, I didn't want you to actually find the inverse. Yeah, I actually need to. We need to on this one. And then we want to state the domain of f and then find its range using f inverse. So we are not even going to be able to graph these. So how do you do range? And it's because you use the inverse to do that. Okay. Now I need to show you this one because there's a special strategy. I didn't leave you a lot of space. I really apologize. I was trying to get this packet just slightly smaller and I forgot I do need the space for these ones. But let's go ahead and do this together. Let's switch out your x's and y's. And I think you guys all need to tune into this one because it is a little trickier than you think. And so I just want to make sure we have the strategy to be able to do this. Okay. Let's go ahead and switch the y's. So what makes this more complicated is the y's are both in the numerator and denominator. And we've got to solve for y. So we've got to get them to the same side somehow. We've got to get both out of the denominator. Okay. So let's start by solving rationals. How do we get rid of this in the denominator? Times it. Good. Let's get it out. So I got to times it to both sides though, right? To keep my function balanced. All right, you guys, let's go ahead and clean that up. What has to happen to the left side? What do you think is a common mistake that I mentioned back at difference quotients that people forget to do? People forget to distribute. So distribute it through. And this ends up giving me a 2xy. And don't let the fact that x's and y's are together scare you off, okay? Because we can get around that. So did those cancel? Yes. How many of you are able to get to this point and recognize? Okay. Okay, what needs to be on the same side? Y's do. So let's move the stuff that doesn't have a y to a different side, and let's move all the y's together. And I don't care which side. So whatever side you choose to put that on, your negatives will be in different places. So you can choose a different side than I do. I'm actually going to minus the y over. So I'm going to make this 2xy minus y, but that means I have to minus the x over. So that's a negative x minus 3. Now what though? Because 2x and a negative y, those don't combine. I'm used to being like 3x plus 5x is 8x, right? What can I do with the y? Who said that? Did you say factor it? Oh, I thought I heard it. I was like, so smart. You can factor out the y. If you guys take out the y, isn't it the same thing as me minusing the 2x and the 1? It's the same thing. In fact, if you guys had a 5x plus a 3x, and I know we can add those, but if I pull out an x, isn't it the same thing as me just saying 5 plus 3 is 8x? That's what you're doing here. You're like just pulling out the y so it's finally isolated, and you now have the two things that were supposed to be added or subtracted. Now what would I do? Divide by 2x minus 1 to both sides, and there's your inverse. Now your inverse might be manipulated a little differently. If you guys had put stuff on different sides, you might have an x plus 3 and a negative 2x plus 1. Your negative might be distributed through the top, or it might be distributed through the bottom differently, but they're the same function. If we were to take this and plug it into that and plug it into this, we don't have the time, but I need you guys, being able to handle it, but I would need you guys to be able to evaluate that and make sure that you could do the inverses. Now, we haven't learned how to graph rationals since last year, and that's a different unit this year. Yet we're expecting you guys to be able to find the range. So how do I do that? Let's go ahead and calculate what the range is. So this one wants the domain of f. So we want the domain and range of f, essentially. Okay? So the domain of f is what? X cannot be what? Negative 1/2. Now I want the range of f. So what do I look at to get the range of f? I look at the domain. We are a little bit out of space, sorry. I look at the domain of f inverse, and that's how I get the range of f. So what would you guys say is the domain of f inverse? X cannot be what? Yep, x cannot be 1/2, so what do I say for the range? Y cannot be 1/2, or we want interval notation. So does that make sense how you would handle a problem like this, where they want you guys to find an inverse of a rational? It's probably the hardest one to find an inverse of. And then you would use the domain of f inverse to get the range of the original function. And we did this all without graphing. Okay. So these would be the answers for your function. Alright, I'm gonna leave that one as maybe a warm-up Friday. I actually am probably gonna have this type of a question on like a little quiz or review Friday, because they usually ask the rational function one if they ask you to find the inverse, because it challenges you. They'll ask it here or the final. They'll for sure ask it sometime. Okay, so maybe we'll use this as a quiz question or a warm-up, and we'll move on to the quadratics. Okay, now that people aren't walked in, because it's already pretty hot in here, I'm gonna go prop that, and I want you guys